We're going to start chapter 16, planar kinematics of a rigid body. So we're moving into rigid body dynamics here. And some of the things to note is we no longer have a point mass. The bodies we're looking at are rigid, so we're not having any flexibility in them. The motion we're going to take to be in a plane. The concept of 3D motion would be an advanced dynamics course, so that's too complex for the tools that we have to work with right now. Types of motion. So when we look at rigid body kinematics, we're going to and in rigid body motion in general, we're looking at basically three kinds of motion. Translation, and normally people think of translation, it's got to be straight, and that's not true. For us, so this is a sailboat in the water, kind of going in circles here. And so how can you tell if a rigid body is in translation? If you draw a line segment through the body, and over the entire path, the line segment stays parallel, that body is in translation. Okay? But we will also have rotation. And so rotation is about a fixed axis. We'll be coming out of the plane. So here we have rotation. You can see my pen. So all particles are on a circular path, with the exception of the particle or points that are on the rotational axis. And of course, then option 3 is a combination thereof. Now, a key fact when we're talking about rigid body motion. So let's take a device here. We'll take my cell phone. It's fairly rigid, so we can model it as a rigid body. And so right here's the camera. Now, if we know the motion of this camera point, so as this moves around, if we knew that exactly, all right, every other point on this rigid body can at most rotate relative to the camera. Okay? Once we know this point, everything else, we can, just by seeing the rotation of the body, we can know what everything else is doing. Okay? Critical point. As we look at rotation, we'll have the following terms, which are not surprising to you. Displacement, theta. Angular velocity, omega theta dot. Angular acceleration, which is omega dot or theta double dot. And we'll just take a moment to note that if the rotation has constant acceleration, the constant acceleration equations still apply. So we can use those. Now let's, with respect to rotation, we need to get our hands on a few equations here. So here I have an xy plane with z coming out of the paper. All right, and here's a particle. And so from the origin here, put in an O. All right, here's a vector r that's not on the z-axis, so this is separate from this. So this goes out to a point or particle that's in the rigid body. And here I have it going on a circular path. So we have omega, all right, and the way we account for rotation is we say that this is in the z, okay? So the rotation is in the plane, and the way we figure out the vector is we cup our hand in the direction of the rotation, and our thumb points in the vector location. So here's something going counterclockwise, and it's going in, we would call it omega z coming out of the page, though all the motion is in the plane. All right? Now, as this thing goes around this circle, at any given time, namely this point here, the velocity is always tangent. All right, so here's the velocity vector. Now, as this thing goes around, the arc length, so from a given point in time to another given point in time, the arc length would be the radius, which is constant here, times the change in the angular position, so delta theta. All right, since radius is constant for going in a circle, speed would be r theta dot, or r omega. And here we see and to make it velocity, we need direction, and that's going here, so tangent. Okay? Now, from your past, you would know then that the velocity, which would be the derivative of this vector r, can also be expressed as omega cross r. All right? Here's the magnitude up here, r omega. Okay? And so if we were to keep in mind that omega comes outside, so if you take your right hand and rotate over to r, your thumb will point in the direction of the velocity. So you have omega coming out of the paper, then you project it over to the r, and you get velocity going that way. Now for acceleration, when we take the derivative of this, we have two terms. And so acceleration is v dot. So we use the chain rule, hold one constant, take the derivative of the other, add the whole thing up. So holding r, we take d omega dt, so that will give angular acceleration cross r, plus, now we'll hold this one and take the derivative of r, so we get omega cross dr dt, but what is this? That's just velocity, this term right in here, okay, which is omega cross r, which I have right there. So alpha cross r plus omega cross r. So how would that work? So this term is just velocity, so we already know omega cross r relative to this point. Here's velocity here. So if we do the cross product, omega cross v, so take your hand, coming out of the paper would be omega, wrap your fingers over, roll it over to the v, that would be omega cross v, thumb points in the direction. That's going back in along r. So this leaves us with the following. Relative to rotation, we have alpha cross r, that's the tangential acceleration. That would be along this, either this direction or that direction. And then we have normal acceleration coming back along the radial direction in there. If you're having trouble visualizing all of this, we have a big picture. So, picture we have the z-axis pointing out at you. Here we have r to this point P, and so here's omega, and then let's bring this down. So here's omega, and then we'll roll. Omega's coming out. Roll to the r. We have the v. Then we let omega go out and roll to the v, come back down the r. And that's shown in this picture right here. So here I have omega coming out. Put your hand up, roll your fingers, and then you get omega cross v coming in. Now we may occasionally use this notation here. What do we have? This is an arrowhead. Okay, that's how you would show these vectors are in the plane. This is one coming out of the paper. And by same token, if we did something like this, this represents tail feathers, so that's an arrow going into the paper. Okay, so as we're going into chapter 14, we basically have 4 sections that we're going to wind up covering. First thing we're going to do, absolute motion analysis. And this is a very straightforward concept. What this is, it's forming an equation for the position. So there will be some point on the rigid body we care about. We're going to have an equation mathematically that describes its position, and you simply differentiate it to get velocity and acceleration. So this is basically a geometry problem followed by a differentiation problem. Then we're going to have a thing called instant centers of rotation, which can be an interesting tool for helping us solve problems. Then we'll get into relative motion analysis. And finally, the very famous Coriolis acceleration, which was actually discovered not all that long ago. It's a very slight acceleration, and we'll show you how you can experience it the next time you choose to ride on a merry-go-round. So we'll stop right there. Next time, we're going to start up an absolute motion analysis.